So it turns out I actually wanted to look at two more problems with you briefly. So how much error can we have in the height of a cone if r is a constant and we want volume to be within 1% of its actual value. And again, what does this mean? We want the error or change in volume to be b equals 1%, 0.01, its actual value. What value? What's it? It is volume. So we've got that helping equation, and we're talking about a cone. Do you remember the formula for volume of a cone? V equals 1/3 pi r squared h. Remember, in this problem, radius is a constant. Pi is a constant, 1/3 is a constant. All we've got is a number times h. So when I think about taking the derivative with respect to h, what's the derivative of a number times that variable? Well, yeah, it's just going to be 1/3 pi r squared, not 2r. It's the that's part of the constant. It's the derivative of h with respect to h. So yeah, my volume now, or my change in my derivative here is a number. This is a number. That's a constant. So we can say that dv equals 1/3 pi r squared dh. No h's here. Don't worry about it. Now, what are we saying? We're saying that dv is within 1% of the actual volume. So we know 0.01 v should equal 1/3 pi r squared dh. And what do we want? We want how much area can we have in the height? Well, that's dh. I want to solve this equation for dh. Yeah, can we do something about that? So I know 0.01 1/3 pi r squared h equals 1/3 pi r squared dh. So I'm trying to get that. Okay, let's divide by all the stuff that's not that. 1/3 pi r squared. 1/3 pi r squared. Okay, and I feel like I'm going to need some more space and say, okay, so I get 0.03. Oh wait, these cancel. And so does that, and so does that. And so what am I left with? I'm left with 0.01 h equals, and these canceled, dh. Well, look at that. The error in the height is 1% of the actual height. The estimated change in height will be 1% of the actual height. And we notice that if we divide both sides by h, we get 0.01 equals dh over h. Aha! What percent is this change in height as with respect to the actual height? Well, it's 1% of the actual height. That's what I'm looking at here, 1%. The change in height, the error in height, is 1% of the actual height when, what was it that we set up originally? We said when volume is within 1% of its actual value, or 0.1%. Ooh, I hope I did that right. Okay, if h is a constant, not r. What error in r can we have if we want volume to be within 1%? No, it's 0.1%. 0.1% of the actual volume. So here, I'm saying the change in volume has to be within 1% of the actual volume. So dV equals 0.001, 0.1% V. Okay? And we're holding h as a constant, and we're still talking about a cone, where V equals 1/3 pi r squared h. This is a constant now. That's a variable raised to a power. I might want to write this as pi h times r squared when I go to take the derivative of both sides with respect to r. If I take the derivative of both sides with respect to r, I'm going to see dV dr on the left, and on the right, I've got this constant, h, times the derivative here, which is 2r. Now, when I multiply both sides by dr, I get this. Now, what did we know about dV? Oh, 0.001V equals 1/3 pi h times 2r dr. And what was volume? 0.001 times 1/3 pi r squared h. And so now I'm trying to find dr. Let's divide both sides by 2/3 pi r h, 2/3 pi r h. And is it pi r? Yes, it's. And so what do we have? Well, the pi's can cancel, and this r can take one of those, and this h takes that. I've got a 1/3 here and a 1/3 there, and so really I've just got 0.001 divided by 2 equals cancel, 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 dr. Where did my spare r go? Thank you. So this is 0.0005 r equals dr. Well, that's percent. So r is within 0.05% of its actual value. So do you understand what we're saying here? We're saying that change in r, that error in r, must be within must be within 0.05% of actual r. I never needed to know what r was or what v was. I can just do this completely notationally. I mean, talk about building logical structures in your brain. I am impressed and amazed. Okay, last problem. The area of an isosceles right triangle must be within 1% of its actual value. What error in side length can we have? So let's think about the area of that isosceles right triangle. That's our good old 45, 45, 90. So base times height times 1/2. Area is 1/2 x squared. Now, I want I want dA to be within 0.01 of the actual area. Okay, so I can put a 0.01. Oh, but I haven't taken a derivative yet. Let's take the derivative of both sides with respect to x. I'll have dA dx on the left side. And on the right side, when I bring down that 2, I might just have x. So if I multiply by the differential dx, I get dA equals x dx. And now I can replace dA with 0.01a equals x dx. And what am I trying to solve for? What's the error in side length called? Oh, the error in side length, the change in side length, is dx. So I want to solve for this. A, I know what A is. That's A. So I can write this as 0.01 times 1/2 x squared, right? A, 0.01, 0.01. So let me clean off some space here and say that 0.01 times 1/2 x squared equals x dx. So when I divide both sides by x, that and that, I get 0.01 divided by 2, which is 0.005 x equals dx. And how do I understand that? The error in measuring the side length must be within, move, 0.5% times of the actual side length. That's what I see there. Or if I divide both sides by x, there it is again. What percent of the actual side length is this error in side length? And we see within 0.5%. The side length must be measured within 0.5% of its side length actual value if we want area to be within 1% of its actual value. Well, that was exciting. Think you can do these? I know, it's kind of exciting. So try this last one on your own. We're talking about the volume of the cylinder, which is pi r squared h. And I want to find the error in volume if h is a constant and r equals 4. Let's say not that. Let's say and r, the error in r must be within 1% of its actual value. So here, the error in r, dr, must be within 1% of r. Find the error in volume. Find dv. And h is a constant. So I need to take the derivative of this with respect to r. So dv dr equals 2 pi r h, right? Because that's a constant. That's a constant. I'm just taking the derivative of r squared. There's my 2r times those two constants. Okay, multiply both sides by dr, and I get dv equals 2 pi r h dr. Well, we know this. 0.01 r times r, and I get 0.002 pi r squared h. And what do we know about dv? Well, hold on. This is called volume. So when I see pi r squared h, that's volume. V equals dv. And so volume, or the error or change in volume, must be within 0.2% of the actual volume. Wow, that's powerful stuff. 1600s, no kidding. All right, take care, everyone.